All right, so today we are going to start the last section of this course, which involves three-phase circuits. I'm getting a call about my car's extended warranty. So as a very, very brief background piece of information here, you actually don't really need to write any of this stuff down. What we have been dealing with for the most part in this class could be quantified as a single phase circuit. And so what I mean by that is that we have some voltage source. Let's call it VP angle theta V. And let's call this terminal A. And this guy is terminal N. And then we have a wire, which in truth will likely have some impedance, but I'm not going to draw that currently because it's not adding anything to the conversation. And over here on the right, we have some load ZL. Okay. So everything to the left of the dashed line represents a source quantity. Everything to the right of the dashed lines represents a load quantity, and everything here in the middle is representative of transmission lines. And in truth, it would be better to call these distribution lines because as you get further into your electrical engineering curriculum, you will realize that transmission lines actually means a very specific thing. So they're called transmission lines in this case because they are used in the transmission of electrical power from one point in a system to another point in a system. But a real transmission line is all about concepts of signal propagation and all that kind of stuff. It's an electromagnetic, it's a branch of electromagnetic theory. So our power distribution lines really wouldn't be considered transmission lines because the frequency of excitation is so slow, right? Power is distributed on at 60 hertz, which means the wavelength of that line is something like the distance between here and Alaska. So it doesn't really look different at different points along the wire particularly. Okay, but anyway, that's the thing you'll learn about in 401. Okay, so in this simple circuit, we have what's called a hot wire and what's called a neutral wire. And this is literally what we have for outlets and stuff like that around the room. Okay. So this would be representative of what's called a single phase circuit, which is what we are most familiar with dealing with. Okay. What we are moving towards is the concept of three-phase circuits. Okay. So in a three-phase system, it might look something like this. I'm going to call this guy A, B, and C. This voltage will be VP angle theta A. This guy will be VP angle theta B. That does not look like a good B. Doesn't particularly matter for right now. And we have our transmission lines. A, B, and C. And then we're going to have our load. Where again, you can split this guy up kind of into 3 discrete sections. Source on the left-hand side, load on the right-hand side, transmission lines in the middle. And in this system, we're going to have an A phase line, a B phase line, and a C phase line. Our transmission line section. So what's interesting about this 3-phase system, this is what's called a 3-phase, 3-wire system, which means it does not have an active neutral. It can deliver 3 times the amount of power as the single-phase system while using only 1.5 times the number of wires. Okay. So from an infrastructure standpoint, distributing power in this way is significantly cheaper than having just a single-phase system, which is why we utilize 3-phase power for transmission of power over long distances. Much cheaper. Okay. There are some other advantages as well that we're going to wind up talking about when we get into the power aspects of 3-phase transmission systems. It might seem a little weird, but the instantaneous power in a balanced 3-phase system is the same thing as the average power, meaning it provides a constant amount of power to a balanced 3-phase load, and we'll talk about what that means in a little bit. And so if you consider an electric motor connected to a single-phase system, what does the power behave like for a single-phase system? The instantaneous power. We covered this effectively a couple of weeks ago. It's got a DC portion, and then there's an AC portion superimposed on the top of it, right? So that means the amount of power that's being absorbed by the motor is constantly changing in time, which means the amount of torque that's being provided by the motor is constantly changing in time, which means the motor vibrates, causing mechanical damage. On a system like this, where the instantaneous power is constant, that means the torque is constant and vibrations are reduced. There is a very specific reason why the 3-phase electric motors that we have in our power lab here at Louisiana Tech, which are literally some of them pre-World War II electric machines, still work with no problems whatsoever. And it's all because they run off of 3-phase power. So the first real topic that we're going to talk about here is the generation of 3-phase voltages. Okay, and I'm going to give this to you in as simplified of a scheme as I can, which is going to require me to draw a very crappy picture, so I'm going to pre-apologize. So I'm going to start with some circles. And I want to make sure I don't like that second one at all. Oh, I feel like I don't, but let's see. I thought using the circle tool would make it easier. I believe I was mistaken. All right, well, I have the outside circle. I will just crap. Okay. I'm just going to draw the inside circle because this is taking far too long. So I apologize. Ian, thank you for your pep talks, but give me a moment to concentrate, please. Oh my goodness. All right, so these are supposed to be two concentric circles. Okay. Yes, something similar to a circle. Okay. And I'm going to have a little section up here. I'm going to draw this conductor in as black and then 180 degrees out of phase with it. I'm going to fill this one in as gray. The colors don't particularly matter. I'm just trying to be consistent with what's actually used with industry. Okay. We're going to call this guy up here A and call this guy down here A prime. 120 degrees physically out of phase. So somewhere around here, we are going to have B, where B is going to be blue. 180 degrees out of phase with that. We're going to have B prime, which is going to be gray. And then finally, 120 degrees physically out of phase with B. We're going to have C, which is red. And 180 degrees out of phase with that. We're going to have C prime, which I'm going to color in gray. Okay. What I am crappily trying to draw here is what's called the stator of a rotating electric machine. Okay. So I'm going to draw some wires here. This is my A terminal. This is my C terminal. This will be my B terminal. And then I'm also going to have a neutral terminal here. And I'm going to connect all of those prime quantities to that neutral. Like so. Okay. So this is what's going on with my stator. Now let's talk about what's called the rotor. So in truth, the rotor is an electromagnet, but I am not going to bother with that because I don't know how to draw it right. So instead, we are going to pretend like we have a bar magnet mounted on a pin in the middle. Okay. That is going to rotate in this direction with some angular velocity or rotational speed, omega. Okay. So A prime, B prime, C, and C prime really represent coils, okay? And so what happens is that when this permanent magnet, which isn't really a permanent magnet by any stretch of the imagination, lines up with the coil represented by A, the amount of magnetic flux seen by coil A is at its maximum, right? Which means that the voltage induced will be at its maximum as well. So we should see something like this. And now I'm going to have to draw sinusoids correctly, which we all know I'm pretty incapable of doing. So I'm going to apologize for that. So this is time. These are voltages. And let's say that time at t is equal to 0 corresponds with when the north pole of that magnet is lined up with A. So that I'm going to get something that's too big. Like this. This is a pretty crappy looking sinusoid, but I'm doing my best, I promise. All right. So this black curve would represent the voltage VAN as a function of time. So let me talk about that real quick. It is literally the voltage measured between this A terminal and this neutral terminal as time progresses. And I'm going to say that it has a value of VPA. So this P subscript is what I'm using to indicate a phase quantity, but we'll talk about that more in a little bit. Cosine omega t. All right. When the north pole of the magnet lines up with A prime, that's when we get our largest negative voltage. Okay. So because there is physically 120 degrees of separation between this coil and this coil, that means that B is going to hit its maximum value 120 degrees later. So it's the exact same waveform, assuming that the coils are identical, so physically identical, but shifted to the right by 120 degrees. So let's see if that's 90. This will be 120. I think. Like so, where VBN of t is VPB cosine 120, excuse me, cosine omega t minus 120 degrees volts, or volts RMS, doesn't particularly matter. I guess it would, since this is a time domain signal, so it's just volts. And then finally, 120 degrees after that. Let's see, 1, 2, 3. Our C phase is doing its thing, where we get VCN of t is equal to VPC cosine omega t minus 240 degrees. volts. So this is how three-phase voltages are generated. Okay. We have a bunch of coils, and every time the flux through one coil is at its maximum is when it's at its maximum voltage. If physically the coils associated with phase A, the coils associated with phase B, and the coils associated with phase C are identical, meaning that they're made out of the same type of conductor, same size of conductor, and having the same number of turns, all of the magnitude of these voltages are going to be the same. And as long as they are physically oriented 120 degrees apart, these phase angles are going to be exactly 0, negative 120, and negative 240. So to unbalance a three-phase voltage source literally requires you to physically construct it incorrectly. So that's not where imbalances are going to come from. Okay. So this is a generation of three-phase voltages. We can represent them as phasors if we wanted to, obviously, or RMS phasors as well, right? Because we know how to go from the time domain into the frequency domain and into the RMS phasor domain. Brandon.
You said that there was no vibration, the power is going to be the same when you have the three phases, but there's still a slight gap in the phase.
When we actually cover the power, we will mathematically show that the power is going to be a constant value. The instantaneous value of the power will be a constant. So we can actually kind of figure things out a little bit here real quick. Let's say that this is 5 with an angle of 0. And this is 5 with an angle of negative 120. And this is 5 with an angle of negative 240. Add those three waveforms together in your calculator real quick. Yeah, in Poland. So any magnitude, it just needs to be the same magnitude. Angle 0 plus that same magnitude, angle negative 120, plus that same magnitude, angle negative 240. 0. So they add together and all of that stuff effectively cancels each other out. So anyway, we'll use that identity in a little bit. So not jumping the shark or anything. Okay, so all right, so we've talked about a balanced three-phase generator real quick here. This is what's called a positive phase sequence, okay? So in the positive phase sequence, A leads B by 120 degrees, B leads C by another 120 degrees. What if omega were spinning in the opposite direction? That's what's called a negative phase sequence. And A lags B by 120, which lags C by another 120. So effectively, it would just change the sign on the phase angles, but all of the other relationships would be identical. Ian.
Aren't AC motors effectively driven by making effectively three-phase square waves for the terminals? Okay, so
yes and no. So let me explain what I mean by that. Okay. So an AC electric motor rotates at a speed that is an integer multiple of omega, depending on how many poles the motor has. Okay. So if we're connected to a 60 hertz system, it's probably going to run at 3,600 RPM, 7,200 RPM, or something like that. Okay. Fixed speed. All right. Now, if you want to make the machine rotate at a speed that isn't an integer multiple of omega, you have to use what's called a variable frequency drive. What a variable frequency drive is a combination of electrical circuits. So effectively, you take your three-phase power and then you put it through a three-phase rectifier, which generates a DC signal. That DC signal is then chopped up by what's called an inverter that spits out square wave approximations of sinusoids at different frequencies that allows you to actually change the speed of the motor. So that's why I said yes and no. And it's not really you're getting a square wave and calling it a sine wave. You're taking parts of square waves and adding them together to make it look pretty sinusoidal with some harmonic oscillation, which does cause a little bit of vibration and stuff like that. Okay. So, but for your basic three-phase motor, like if we went into the power lab and hooked things up, what's coming out of the wall is a sinusoid, right? It's going to run off that, and it's going to run at pretty much the exact same frequency unless we put a load on it, and then that's just going to cause it to slow down a little bit, and then steady state, it's going to rotate at that frequency forever. When you hook up a VFD and you're doing some analog signal processing, that's where that pulse width modulation to generate sinusoidal waves that are pieced together square waves comes from. Okay. Excuse me. So this is how our three-phase voltages are generated. We've talked about positive phase sequence, which effectively just means omega is counterclockwise and we get negative phase angles. For a negative phase sequence, omega is clockwise and we get positive phase angles. Okay. In this class, we're always just going to deal with a positive phase sequence. It really literally means nothing except that the motors or the generator is spinning in the opposite direction. So it makes no changes whatsoever on our analysis, except that all of our phase angles will become positive instead of negative and vice versa. All right. So let's now talk about source and load configurations. All right. So the first thing that we're going to talk about is the Y connected source. You may see it written out as WYE or literally just capital letter Y. Okay. So for a Y connected source, it's going to look something like this. Okay. And let me draw this guy right here as well. So I'm going to label my voltages, and I want to talk about how I'm going to do that. I'm going to use what's called a double subscript notation. So I'm going to call this voltage right here VAN, where A is the positive polarity terminal and N is the negative polarity terminal for this voltage. Okay. Whenever I am on the source side of the circuit, I'm going to use lowercase subscripts. Whenever I'm on the load side of the circuit, which will come about in a couple of minutes, I'm going to use capital letter subscripts. Okay. So this would be voltage VBN, and this would be voltage VCN. Okay. Now, I find that drawing this shape is a pain in my butt. I don't particularly like to do it. So instead, I may choose to draw this three-phase source like so. Here's A, here's B, here's C, here's N. So that this would be voltage VAB, excuse me, VAN, sorry, getting ahead of myself. This is voltage VBN. This is voltage VCN. The neutral connection here is optional. It's not required literally at all. Okay. So you can absolutely have a Y-connected source with no neutral. There's nothing wrong with that. But when we get into our circuit analysis, we'll find out that it can play a very important role. And it's actually got pretty interesting characteristics. Okay. So now I'm going to hit you guys with some definitions. Okay. And honestly, this is one of the hardest parts of the class. I don't think it should be because I feel that I am explaining things fairly straightforwardly. But this is probably one of the easiest places to get confused because I'm going to talk about things on concepts of phase quantities and line quantities. And if you don't understand what a phase quantity is versus a line quantity, you're obviously going to get confused. Okay. So the first thing that I want to talk about are phase voltages. Okay. So a phase voltage is simply the voltage drop over one phase of a source or load. So for a Y-connected source, we have three phase voltages. VAN, VBN, and VCN. Line voltages are the voltage drops between or over transmission line terminals. Of a source or load. So I'm going to use, oops, slightly too far, a different color here to illustrate these. All right. So this potential difference, VAB, represents a line voltage because it's the voltage measured between the two transmission lines. Okay. So we could see that show up here as well. We'll have a line voltage VBC measured between transmission line terminal B and transmission line terminal C. And similarly, we'll have a voltage VCA measured between transmission line terminal C and transmission line terminal A. So VAB, VBC, and VCA are our line voltages. Now, some textbooks / engineers call phase voltages line to neutral voltages because they're measured between the line and neutral. Some engineers call line voltages line to line voltages. I am going to use the nomenclature of phase voltages and line voltages, okay? Now, I want to talk about phase currents. Okay. A phase current is simply a current through one phase of a source or load. Okay. So I am going to adopt the convention here that phase currents are going to be defined such that they flow from the positive polarity terminal to the negative polarity terminal. Okay. So that means I would have a phase current like so, IAN, a phase current like so, IBN, and a phase current like so, ICN. And I'm going to draw them here as well. It should be B. All right. Now, there are also line currents. Okay. But a line current represents the current flowing through a transmission line. And since our source isn't connected to anything, there's actually not a way for us to represent line currents on my current diagram. So when we actually start looking at whole three-phase systems, I'll bring up that concept of line current again, and we'll talk about its full definition. Okay? So for all of the different configurations that we're going to talk about today and probably a little bit next week, we're going to need to be able to identify phase voltages, line voltages, and phase currents. Those are the tricky ones. Line currents are easy because it's always just the current through the transmission line. There is no remote ambiguity there. Okay. So, how do you guys feel about the quantities that we've defined for this Y connected voltage source? Anything seem wonky or anything? Alexis?
Any particular reason you swap the signs of the VCA?
So I didn't swap the sign of VCA. I'm always taking it So it's going from A to B, B to C, C to A. So the C is the positive polarity terminal because it's the first letter in the subscript. The A is the negative polarity terminal because it's the second letter in the subscript. So that's the convention I'm using. First letter is the positive polarity terminal. Second letter is the negative polarity terminal. I don't know why they don't call it VAC, positive polarity on top. They just do VAB, BC, and then VCA. And we're going to develop some transfer. Actually, I guess I probably do know why they do it that way. And it's because we're going to develop some transformation from phase quantities to line quantities that will use that particular order of phases.
Also, I feel like throwing an extra square than AC.
I didn't even think about that, but that's quite true. Yeah. Calling another thing AC would confuse the bejesus out of me. So yeah. All right. So this is one of our two potential source configurations. All right. Our next configuration, and I'm just going to go to another page to make sure I have enough room, is the delta connected source. It will make a shape of a triangle. Absolutely right. Surprise, surprise. Engineers are lazy and predictable. So let's call this guy terminal A, this guy terminal B, and this guy down here terminal C, which would give us voltages VAB, VBC, and VCA. An alternative way to draw a delta connected source is like this. So let's call this terminal A, this terminal B, this terminal C. Giving us voltages VAB, VBC, and VCA. There is no neutral in a delta connected source. Yes, so let's talk about that. Actually, that's the next thing that we were going to do. So our phase voltages here will be KB, VBC, and VCA, because they absolutely represent the voltage drop over one phase of the source. But as Brandon pointed out, our line voltages, which I believe I used this green color, are VAB, VBC, and VCA as well. So for a delta connected source, and we will see shortly a delta connected load, the line voltages And the phase voltages literally represent the same quantity. Okay. Later on, when we're looking at full systems, we'll see that for Y-connected loads and sources, the line currents and the phase currents represent the same quantity. But anyway, we'll get there, okay? So just for the sake of argument here, let's call this guy VAB, this guy VBC, and we can do the same thing here. All right, and then our last quantities of interest will be our phase currents, where again, I'm adopting the convention that phase currents are flowing from point of high potential to the point of low potential. And so that means we're going to have this guy, which will be IAB, this guy, which will be IBC, finally this guy, which will be ICA. On this diagram, here's IAB, here's IBC, here's ICA. Everybody okay? Anything seem wild or wacky? All right, so let's move along to our loads, right? So we only have two options for sources, a Y connection and a delta connection. We will have the exact same two options for our loads. We're going to have a Y connected load and a delta connected load. So for our Y connected load, I'm going to call this terminal A. And I drew that too crappily. Try that again. Here's B. Here's C. So I'm going to call this ZYA, ZYB, and ZYC, where these impedances do not have to be equal. Okay. If they are not equal, we have what's called an unbalanced load. If they are equal, we have a balanced load. Okay. So let's identify our phase voltages, line voltages, and phase currents. Oh, actually, the alternative way to draw this, should introduce that. And we do have the possibility of a neutral conductor. So I'll put that guy in there. Would be something like this. A, B, C, and N. VYA, VYB, VYC. Okay. So phase voltages, what do we think they're going to be? Exactly right. VAN, VBN, and VCN represent our phase voltages. So that would be this guy, this guy, and this guy, or this guy, and this guy. That doesn't, C doesn't look good to me. On this diagram. What are our line voltages going to be? Yeah, so just the exact same thing. Effectively, all of these quantities are going to be literally the exact same thing we had on the source side. They're just going to have capital letters, right? That is a fantastic question. Let me answer it when I finish writing this down. So, if our transmission line does not have an impedance, meaning that it's a lossless transmission line, then the line voltages on the source side, or the quantities on the source side are identical to the quantities on the line side. However, if our transmission lines do have impedances and cause losses, they will not be the same quantities. We're going to talk about that when we get into our circuit analysis. That's a very good question. So we can call this voltage here VAB, and it's a little easier to see them on this side, so I'll do VAB, VBC, and VCA. And then finally, we are going to have our phase currents, which will be IAN, IBN, and ICN. Like so. Anybody have any questions regarding our Y connected load quantities? All right, so our last permutation is then the delta connected load. So we're going to have that triangle looking shape. Like so. I'm going to call this guy Z delta A, Z delta B, and over here, Z delta C. Our, in my opinion, easier way to draw these guys looks like this. C giving us Z delta A, delta B, and Z delta C. And from here, we can identify our phase voltages, our line voltages, and our phase currents. So much like we saw in our Y-connected load, the quantities for our delta-connected load are literally going to be the exact same things symbolically, except that we're going to use capital letters because we are on the load side of the circuit. So that means we're going to have phase voltages of VAB, VBC, VCA, line voltages of VAB, VBC, and VCA, and finally phase currents of IAB, IBC, and ICA. And I'll take a moment here to illustrate those. Here's IAB, IBC, ICA, or IAB, IBC, ICA, VAB, VBC, VCA. Okay. So we have two different ways that we can connect our three-phase voltage source and two different ways that we can connect our three-phase loads, giving us possible combinations of Y delta systems, YY systems, delta delta systems, and delta Y systems, right? Where when I say that, the first term tells you how the source is connected, and the second term tells you how the load is connected. So I am going to, this is going to be the last thing we do today. Surprisingly little math for today. I promise you I'm going to make up for it. Yes. So to best answer that question would require us to look at some analysis to see what role the neutral plays, okay? But the short answer is you can absolutely have a delta Y or a Y delta where the neutral's probably just tied to ground or something like that. So let's say I'm going to take a moment here to draw a system. Actually, I drew that one backwards. Minus plus. A, C. I've already made a mistake here by putting capital letters on my source side, so I apologize for that. I'm going to call this ZWA, ZWB, ZWC, representing our transmission line impedances. So is this load Y connector to delta connected? Alexis, is the load Y connected or delta connected? So the presence of a neutral terminal here, even if there's not a wire going to anything else, makes this guy have to be a Y connected. So if all three of the quantities are tied together at one node, it's definitely a Y. Okay. I'm going to call this ZYA, ZYB, ZYC. Sunny, my source, delta or Y. Source is delta. Absolutely right. So this is going to be VAB, VBC, and VCA. Okay, so all we are going to do here is a simple exercise in identifying things correctly. So Cheston, what are my line voltages at my load going to be? So VAB, okay, so that's one of them. And let's label it real quick. That would be this guy right here. I got two others. VBC. VCA, right. And I'm using capital letters because I'm on the load side of the circuit. Mr. Bodie, what are my phase voltages on the source side? Okay, sure. So lowercase a, lowercase b, sure. V lowercase b, lowercase c, and v lowercase c, lowercase a. Yeah. So the source voltages are always the phase voltages. Okay. Sarah, what are my line voltages on the source side? Exactly right. EAB, BBC, and VCA. Let me just label them here. All right. Coy, what about my phase currents on the load? So IAN, BN, and ICN. Alexis, what are going to be my phase currents in my source? Yeah. No. So phase currents, this is why we're spending a day on jargon and nomenclature, because this absolutely confuses a lot of students. Okay? So phase currents represent the current that's flowing through one phase of our source. Okay. And we have adopted the convention that the current is flowing from the positive polarity terminal to the negative polarity terminal. So if this is one phase of our voltage source, our phase current would be IAB flowing down, IBC flowing down, and ICA flowing up. All right, the last thing here that we've talked about previously would be our phase voltages at our load. Christian, take a crack at these, please, sir. Right. VAN, VBN, VCN, and those would show up here. All right. So the last thing that we could possibly identify on this jarbled mess of information would be what are called our line currents. All right. And they don't really fall under the source side or the load side. Okay. So our line currents, by definition, are currents flowing from the source to the load through our transmission lines. So I'm going to do these in blue. Sorry, I went too far. So that would be current I, lowercase a, capital A, current I, lowercase b, capital B, and current I, lowercase c, capital C. So transmission line currents are all defined as flowing from the source to the load, which is why they have the lowercase letter first. So A, B, I, C, C. So generally speaking, yes, but let me clarify exactly what I mean by that statement, okay? So if we look at this diagram, the impedance ZWA looks like it is in series with impedance ZYA, and therefore our line current IAA is the same as our phase current IAA. Now, if we had a Y connected load, though, we would find that our line currents are negative of our phase currents at the source because of the convention that we have adopted where current is flowing from the positive polarity terminal to the negative polarity terminal, right? So our phase currents in a Y connected load would be flowing to the left. And so that's why we would have to make sure to include that negative sign. So generally speaking, for Y connected systems, the phase currents and the line currents represent the same thing, but we might have to include a negative sign to change the direction just because of the convention that we happen to have adopted. Okay. All right, so it's 12:15. I was finished for today anyway. So on Monday, I have to look at my schedule. There is a faculty candidate who is coming to campus for interviews and all that kind of good stuff. And I have to participate in that interview process as well as take them out to lunch. I know for a fact that that conflicts with my electronic circuits class, which is the one I have directly after this one. So I am not able to hold that class. I'm not sure yet if that will conflict with me holding this class. So I may send you all an email over the weekend that's going to say, hey, we are not having class on Monday. So that is a very distinct possibility. Okay, so I'm just letting you guys be aware of that now. If we are unable to physically have class, would you like to watch one of my previously recorded videos on this stuff, or would you like to just take a pause for a day and we resume on Monday, or excuse me, Wednesday? Okay. All right, fair enough. All right, so if I'm unable to do class, to hold class on Monday due to the commitments with the meeting with the other faculty candidate, then we'll just pick up where we left off from today on Wednesday. I'm not guaranteeing that I'm going to have to cancel class. I have to look at my schedule. I may be able to get away with just ending class 15 minutes early or something like that. So anyway, all right, see you guys potentially on Monday, definitely on Wednesday for sure.